titled Evaluation of Inverter Topologies for High Power Medium Voltage Aircraft Applications. This is the outline of our presentation. I'll just dive into the topic. So there have been some reports in the recent time regarding the use of electric power for propulsion of small aircrafts. Okay, and in one of those reports, this DC bus voltage rated level of 3000 volt has been mentioned. Okay, we believe there is the choice of the DC bus voltage is very important. It is very likely that the DC bus voltage will be produced from an AC generator, and also in the electrical propulsion will be used to drive an AC electrical motor. And for that reason, AC to DC conversion and DC to AC conversion will be needed. Very likely these power converters will use semiconductor power devices which are designed for a standardized voltage level. In the portfolio of various power semiconductor companies, you will find power devices rated at 1.7, 2.5, not so much, but the 3.3 kV and the 6.5 kV are strongly, there is a strong presence of devices for those voltage levels. In the last decade, there has been a lot of progress into industrializing and producing real products of these wide bandgap devices for high voltage using mostly silicon carbide technologies. And typically the trend in the industry is to replicate the pre-existing rated voltage levels and produce devices with similar voltage levels. Already in production there are 1.7 kV silicon carbide devices. There are many reports referenced also in the paper of 3.3 kV industrial products, and also there are some companies that are exploring the market with 6.5 kV devices. So now the question is, what would be the optimum choice of a DC bus voltage for such an electrical aircraft that could maximize the voltage utilization of these silicon carbide devices? I have listed a few issues here which could contribute to the optimum choice of this. I'm not saying that we know already what the optimum level may be. Obviously, the choice of silicon carbide would allow for faster switching, but in conjunction with existing layouts and much faster DVDTs, when you try to turn off faulty currents much faster, you end up with additional overvoltage generated. However, silicon carbide has been reported to have better avalanche behavior, so for that reason the typical voltage safety margin, which for silicon devices would be something in the range of half of rated voltage up to 60% of rated voltage, could be used for the application. We could go a bit higher with silicon carbide. Working at high altitude means that operation under potential impact of cosmic rays may have to be taken into account, but there are some positive aspects also with silicon carbide needing larger energies for triggering this sort of accidental turn-ons. On the negative side, the turn-off gate to source voltage is significantly smaller for silicon carbide than for silicon, which means that obviously you could get some other types of parasitic phenomena that will turn on accidentally the device. In a nutshell, we say that this voltage utilization factor needs to be carefully considered. In our approach here, we assume that we would be using a 3.3 kV device with a voltage utilization factor of 0.75, which would give us DC bus voltage of not more than 2.5 kilovolt, okay? And also for these reasons, we will be using only two-level power module designs. And obviously we can, in order to meet the high power requirements and eventually the high voltage, high current requirements, we can allow operation in parallel or in series of these various modules, okay? The other issue we have seen that it's not currently solved is the issue of power quality standards. Most aerospace standards are specifying DC bus voltages of up to 270 volt. The 540 volt is basically an extension of the 270 volt bus voltage, and we assume that we can scale up the limits for the allowed harmonic emissions in the same way, in the same proportion with the voltage. So if we assume a 2.5 kV DC bus voltage, we can then shift this whole envelope upwards by about 19.3 dB. What this means is that we can have, for example, if we assume our converter is operating at 40 kilohertz, we can have then harmonics of up to 3.57 volt, 56 volt RMS or 5 volt peak, and at twice the switching frequency of 1.28 volt RMS, 1.8 volt peak. Okay, and these limits then can be used to design the DC bus smoothing circuits. One thing I want to draw the attention to is the profile of this envelope. We could see that perhaps this envelope has been designed in an era where power electronics were not switching very fast. It is very likely designed for 12 pulse or 18 pulse diode rectifiers, and we could see that in fact operation with silicon carbide devices which go beyond 50 kilohertz, which is this point where the limit for harmonic emissions increases from 20 dB per decade to 40 dB per decade. What this means is that you don't gain so much into the reduction of the size of the filters. In order for taking advantage of switching faster, you probably need to employ a filter with a higher attenuation, okay? So what we did, we have shortlisted a few converter topologies to do our investigations, and considering the fact that the 3.3 kV is a relatively new technology, we try to keep the power converter topology as simple as possible. So we started with two-level converters, and we took into consideration the fact that we would want a higher resilience to a phase loss, so we assumed arrangements where the neutral of the supply, in this case for this active rectifier, should be connected to the DC link midpoint, okay? The point is that whenever you do this connection, you lose the advantage of switching ripple cancellation between line to line, and for that reason, it makes sense to take advantage of the interleaving. So if you adopt a triangular carrier 120 degrees displaced between each of these three legs, you could then obtain some reduction, some significant reduction in the common mode voltage generated by this particular type of converter. Okay, the disadvantage of this converter is that you end up with the supply frequency current passing to the DC link capacitors, which may request an increase of this capacitance. If you want to maintain that capacitance low, you could adopt this four-leg configuration where the additional fourth leg switches with 50% duty cycle, which also has a role not just on reducing the DC link capacitance, but also further reducing the common mode voltage. Okay, forgot to mention that once we shortlisted the candidates for our candidate topologies for our converter, for this particular study, we only selected the generation of common mode voltage as a criteria to evaluate the various topologies. We assume that we need more power than a single device can handle, so you can either have a connection of parallel converters, or you could have also series connection of converters. Once you need to do the paralleling, you can also explore any advantages that operation in interleave mode can give. In this particular case, we have two three-phase converters, each of two levels. And by adopting the interleaving of the carrier signals for the two three-phase bridges, you obtain a significant harmonic cancellation in the current as seen by the AC generator, and also the quality of the voltage in the point of common coupling improves significantly. Okay. In addition to that, you also obtain a significant reduction of the common mode voltage, but the problem is that with parallel connection on the AC side and DC side, the interleaving will result in a relatively large circulation current at the switching frequency, and for that reason you may need to have a relatively large AC side inductance, or rely on some coupled inductances, which are not so good in case one of the rectifier's stages needs to stop operating. Then you could cause saturation in those coupled inductances. The other option here is to use, especially if you have access to isolated windings of this generator, is to actually connect H-bridge inverters with a series connection on the DC side and rely on the isolation on the AC side. In this particular case, you end up with a twice the supply frequency DC bus voltage ripple. But the nice thing about it is that all these ripples are 120 degrees displaced. So although you may end up with a relatively large ripple in the individual DC links, overall the DC bus voltage ripple caused by the three DC links will cancel out. Also, the interesting part is that as long as you can guarantee a very good insulation of the windings of the three phases in the generator, you can obtain a significant reduction of the AC component of the common mode voltage. Obviously, the DC bias due to the series connection of the DC buses remains when you adopt the interleaving. Okay, you could go for the three-phase approach, whereby you can have an AC generator. Assume for aerospace you want to operate with higher stator frequency and higher number of pair of poles, and for that reason you could define areas in the stator of the generator where you could have stator windings which can be isolated from each other. So different sections producing in this particular case a six-phase voltage system. Each phase voltage system can supply one of the bridges which are connected in series. You could adopt a similar situation with this arrangement, whereby you can have two three-phase supplies which are isolated, and for that reason you could end up with a significantly smaller circulation current, because obviously you have isolation on the AC side. The nice thing about this one is that if you adopt 180 degrees carrier signal for the second bridge compared to the first one, and if the modulating waves have been chosen such that phase A in the bridge 1 it's in opposition to phase A in bridge 2, the pulse signals produced by the two bridges generate a common mode voltage which at any particular point is in opposition to the first bridge, and therefore you obtain complete cancellation at any instant during the operation of this converter. Okay, we also explore the situation whereby having such a generator with multiple windings, you may develop a hotspot, and what you want is to change the loading, the current loading of the various windings, which will result in different amount of power absorbed from the different windings, and for that reason different power delivered to the DC link by the series connected converters may result in a different sharing of the DC link voltage, while the DC link current obviously needs to remain the same. And we have demonstrated that this can be achievable, and you could obtain a mild change in the current distribution. In this particular it was 8%, which resulted also in a mild imbalance of the voltages, but this is fully controlled, and you could still continue to generate a relatively high DC bus voltage as required. Okay, so this just shows the flexibility these sort of arrangements are offering. So now, unfortunately, it's time for us to conclude. So we looked at the design consideration for choosing converter topologies for a medium voltage high power inverter for aircraft applications. We discussed the aspects that would determine the right choice of the DC bus voltage. We also looked at how we can rescale power quality standards. We investigated a handful of converter topologies, mostly relying on two voltage level modules that would be good for scaling up either in voltage and also current and power to obtain multi-megawatt power levels at more than 2 kilovolt DC bus voltages. Yes, and unfortunately we did not have more time to do for this initial stage in this paper than to just show the behavior with the generation of common mode voltage, which is very important into minimizing bearing currents and any EMI related issues. So we have seen that it is possible with one of the more complex solutions. You could eliminate completely common mode. We want to acknowledge the financial support we received from Clean Sky 2 under grant agreement A21500. Thank you.